It's called the divergence theorem. Good name, because basically you find the divergence of a vector field F. So what does it do? Well, it has a nice little niche market. The divergence theorem gives us an alternate way to find one of these guys, these surface integrals. These particular surface integrals, what you have is you have a vector field, and in this vector field there is a surface. And every point on that surface, I'm doing it with my hands, every point in that surface, right, it has a vector leaving it. And what you're trying to do is basically sum the entire vectors together. So if you had a surface and this entire surface integral, say, came to 0, that would kind of tell me that all the vectors that are going up the way would be cancelled by all the vectors going down the way. It would be almost like an equilibrium situation. But if it was positive, then that would tell me that the flux is positive, means, I believe, more stuff is coming into the world than is leaving. And if it is negative, more stuff is entering the world than leaving. And the stuff we're talking about could be like temperatures or magnetic fields or whatever it might be. So how do you calculate, or what's this thing called, the divergence theorem? It's this guy here. So I'm going to draw a little, try at least, and draw a little picture of what this looks like. Imagine that you've got a surface in 3D. There you go, right? That's a curved surface. That's the guy we call S. Now, if you take that curved surface and you look at it, and essentially, if you drop it down to the floor, oh, that looks like a piece of bread, right? That region, that 3D region, we call E. And according to the divergence theorem, the double integral over this surface is the equivalent to the triple integral of that entire region, that triple integral, yeah, gotcha, of the divergence of F. And it's rather weird that that's true, but nonetheless it is. So what we typically get in these questions is that you're going to be told what the vector field is, and it's going to be, you know, X, Y, Z, some X, Y, Z, X, Y, Z. So in this case, these are just placeholders for functions of X, Y, and Z, PQR. And you're going to calculate the divergence of it. That's a little difficult, that says dp. But the divergence, remember, it's just basically the dot product of the gradient vector with the vector field. So it's basically that guy, the gradient operator, dot product with F. That's what that's equal to. And you're good to go. So this double surface integral turns into a good old-fashioned, haven't seen it in ages, triple integral. So what do the regions E look like? Well, the most common regions you get, because there's very often 3D surfaces got bits to it, like a sphere would be a 3D surface. The surface would be the surface of the sphere, and E would be all the points inside it. But the most common shapes, not all of them, are boxes. So you can imagine a box, 1, 2, 3, 6 sides, and the surface area would be all the vectors entering or leaving the 6 sides of that box. And in that case, this dv and the limits of integration would simply just be numbers, and dv would be a good old-fashioned xyz guy. If the surface happens to be a complete sphere, then we enter spherical coordinates. And these guys here, remember, squiggle 0 to pi, theta to 2 pi, and rho 0 to a, where rho represents the radius, and I'm calling the radius a, so I've got a number I would put here. And you do all the usual conversions, which I've forgotten half of them, but I wrote that one down. And most importantly, isn't this the conversion vector? So what does dv turn into when you go spherical? It's rho squared sine squiggle d rho d theta d phi. And sometimes you get a surface that generates a volume, a 3D volume, and where cylindrical coordinates work. And if it's cylindrical, thetas, r's, and dv. So that's pretty much the big picture. Let's jump right into specifics. Our first question has a vector field that's x, y, e to the z, x, y squared, z cubed, and negative y, e to the z. And we're being asked to find the surface integral, this guy. Actually, that's what we're going to be asked to find in all 8 questions. Oh, and by the way, for some reason, people in physics might have heard this term. When you get this number, right, this thing, whatever it ends up being, this value, it's called the flux of the vector field across S. So evidently people in the engineering world, maybe electronics or whatever, and want to find a thing called flux. Just curious, has anybody ever heard a flux being used in physics or electronics or anything? Is it a term you've not come across yet? FLUX, the flux of something?
Only in Back to the Future.
Okay. I'm assuming then eventually it will appear in its, in its version that it does. But that's true about all sci-fi movies. If you watch sci-fi movies, they do actually use scientific terms, even in ways that don't necessarily work, but they still use it. So I'm assuming from that context, flux does mean something to someone. So what have we got here? Well, we've got this guy is what we want, and they tell us who S is. S is bounded by, and they go and tell us, well, they tell you it's the coordinate planes, and the guys that they tell us are x equals 9, y equals 2, and z equals 1. And what they don't tell you, but they should have, and I'm not quite sure if I just made it, have to assume this, that you need to have a start value or else the integrals don't mean anything. So basically, that's the limits of integration caused by this box. Okay, let's see if we can move this a bit more. Right, well, we're ready to set it up. First thing I would do is calculate that fella on its own. So it's the derivative of p with respect to x, partial derivative of q with respect to y, partial derivative of r with respect to z, and that's p, your q, and your r. So the divergence of f is going to be, if you differentiate this guy with respect to x, you get y e to the z. If you differentiate this guy with respect to y, you get 2xy z cubed. And if you differentiate this guy with respect to z, you get minus y e to the z. And we are kind of lucky here algebraically, because these two cancel out, and all we're left with is that guy. Now, according to the divergence theorem, the guy we're looking for, which is this, can be found by calculating this guy. So the surface integral, this fella, is equal to a triple integral of the divergence of f dv. Well, the region E is this box. So it's going to be the integral in no particular order from x equals 0 to x equals 9, from y equals 0 to y equals 2, and from z equals 0 to z equals 1. the divergence, which is 2xy z cubed, and dv, because of the order I've decided to do them, is a dz, a dy, and a dx. We are darn close to finishing this question. So let me ask you one thing before we kind of move on. Is this integral separable?
Yeah.
Right. So wouldn't you, and that's the last bit I'm going to do, wouldn't you, for ease of calculations, just find the integral from 0 to 9 of 2x, the integral from 0 to 2 of y, and the integral from 0 to 1 of z cubed? And I'm not going to do that. Would you agree that's just good old fashioned? You could do that in your sleep calculation. So what this has allowed us to do, this really clever niche market, I mean, it only does one job. It allows you to find an easier way to get a double integral of a surface, right? A surface integral. And it does it by converting it into, hopefully, and it should be, a simpler triple integral. Kind of cool, right? Kind of a nice way to do things. Moving on to, oh, by the way, in case you're using this as a practice question, 81 halves is what you get. Okay. The next one is also a box. Won't do this one quite as far. You've got your usual flux, which is just another name for this surface integral. And the vector field is x squared yz, xy squared z, and then xyz squared. And the region is described in terms of a box, and the box goes, x goes from 0 to a, y goes from 0 to b, and z goes 0 to c. So can you imagine that when you're finished, the answer is going to have A, B's, and C's in it, because A, B, and C are just constants, right? They just don't tell you what it is. Right, we've pretty much got everything we need. Let's do the working now. The divergence is going to be the derivative, partial derivative of p with respect to x, then the guy with y, and then the guy with z. Well, he's p, he's q, he's r. If you differentiate this guy with respect to x, you get 2xyz. If you do this guy with respect to y, guess what? You get 2xyz. If you do this guy with respect to z, guess what? 2xyz. And so the whole answer becomes 6xyz. Oh, here's a question for you. It hasn't happened, might never happen, might happen in your version and not mine. If the divergence is 0, because it could happen, could you imagine all the terms just cancel out? If the divergence is 0, what will be the answer to this? I don't need to actually do any work. I know the answer. If the divergence is 0, what's the answer to this?
It's got to be 0, right?
Right. It's got to be 0. Let's move on then. Well, all I'm doing now is setting the thing up and leaving it alone. It's going to be from x equals 0 to a, y equals 0 to b, z equals 0 to c, and the divergence is that guy, and it's going to be dz, dy, dx. Right. Would you agree that's also variable separable and pretty easy to calculate? Your answer is just going to have a lot of x's, a's, b's, and c's in it. That's it. Any questions about 2, or is that good enough? You'll be able to finish it yourself. We're good. Okay. Well, let's move on to a much more difficult version. And in this case, as always, you're going to be asked to find this fella. And the vector field F is pretty unremarkable. That guy. S, on the other hand, the surface is a sphere, center the origin, which is the only place it will be, radius 3. Okay, good to go. Let's find the divergence. The nice thing about these questions is that they do have a process. You kind of follow the math, and the steps are pretty consistent. This guy with respect to x gets you 3x squared. This guy with respect to y only gets you 3y squared. And this guy with respect to z gets you 3z squared. Now, since this surface is a sphere, which means the volume then is the inside part of a sphere, right? It's spherical coordinates. It just is. So I'm going to combine these together. And hopefully we remember that in polar coordinates, isn't x squared plus y squared plus z squared rho squared? So I'm going to make sure everything is in terms of spherical coordinates. Well, in spherical coordinates, the variables in no particular order, it's rho, and the radius of this is 3. So I guess I should put them here. Rho goes from 0 to 3. If the radius was 10, rho would go 0 to 10. And then we go theta. And then we go squiggle. Okay, in spherical coordinates for a complete sphere, which is what we've got here, what are the start and finish values for theta?
Two pi.
Correct. On the other hand, for phi or squiggle, what are the range for an entire sphere?
I think some 0 to pi.
Pi.
Agreed, 0 to pi. Now, the curl goes in here, or sorry, not curl, the div goes in here, which is 3 rho squared. Can anybody remember? I'm going to find it here in a minute, but can anybody remember off the top of their head? And I did have it written down somewhere. Oh, here we are. Ah, hide it. What does dv turn into when you do a spherical coordinates? You know, like if it was Cartesian, you would get r, dr, d theta, dz, right? But when it's spherical, it's a little bit messier, isn't it?
B squared sine phi.
So let's see it. Phi squared, sine squiggle, phi. And in the order I'm doing it, it's rho, and it's theta, and it's phi. Well, that's the meat, the bread and butter of this integral. It can be, and it certainly can be, and will be combined into 3 rho squareds, rho 4, I should say. is this fella separable? Is this integral? Can you separate each of the variables into separate integrals?
Yeah.
And the split is going to be that guy, I'll give him the 3 as well, gets him. Poor theta. Well, if there's nothing there, you get 1. And the squiggle guy at the 5 fella, this one here, he does get something at least. And he gets the sign of that guy. And that's where I'll leave that one. Would you agree? You could finish that. That'll get you a negative cosine. That will get you 2 pi, and that will get you whatever it gets you. And according to whatever sign, that's what the final integral, if you take it to the end, would be. How about 3? Any issues? Just a little bit messier, that's all. Okay, 4 is not a box and is not a sphere, but we're still going to find the flux. And the vector field that the surface is basically living inside is e to the y tan z, comma, x squared y, comma, e to the x cosine y. That guy's p, that guy's going to be q, that guy's r. And the surface is z equals 7 take away x take away y cubed. X goes from 0, negative 1 to 1, I should say. And y also goes from negative 1 to 1. Now, the only guy I guess I don't have, and I'm going to make the assumption here, that when you are writing down the limits of z, that it's going to be 0 on this side and this guy on the other side, because you're projecting the thing onto the floor, and when you project something onto the floor, the z will be 0. So that's my argument for that. So we basically have the limits of integration. The surface of the main curve part basically just gave me the limits of integration on z. These two we were told, right? I didn't need to calculate them, they just told me what it was. So let's find the div of f, because that's part of the process. Partial derivative with respect to x, y, and z. Well, if you do that guy with respect to x, since there aren't any x's, you get 0. If you do this middle one with respect to y, you get x squared. And if you do this end guy with respect to z, you get 0. Well, the divergence of f is just x squared. So we are pretty much ready to rock and roll. The surface integral, FDS, is going to be a triple integral. Now, since this guy here has x's and y's in it, that tells me this one has to be done first. So that is done. After that, these both contain numbers, so I'm just going to choose to do y next and choose to do x last. And since I'm doing z, then I'm doing y, and then I'm doing x, that's that guy. And the div goes in here, which is just x squared. Now this integral is definitely not separable. Not even in a good day is that ever going to be separable, at least in the first phase of it. So I'll just take it a little bit further, then I'm going to stop. If you integrate x squared with respect to z, x squared is considered a constant, so all you get is x squared z, evaluated at 0 and at 7 take away x, take away y cubed. Then a little bit more, I think. You get x squared times that guy minus nothing. So I won't write it down at all. So you get that. Okay. Right, let's talk about what I would do next, but I'm not actually going to do it. I would not integrate this guy, not at least the way he's written. What should I do next before I even think about integration? What should you do algebraically to this expression before you start thinking about integrating anything?
Just distribute the x.
That's it. And what you will end up with is one ugly, excuse me. Let us shut my phone off. What's that saying? Yeah, what you're just going to end up with is one ugly polynomial, right? It's not, integrating polynomials are not difficult. They're just long and ugly fractions, but they're not that bad. And according to Leibniz, this one eventually ends up being 28/3, which is okay. It's not the horriblest thing I've ever seen. Oh, any questions about that guy? Okay, and you begin to see a theme here, and the theme is you've got a surface, find out what the limits of integration of that surface are, right? What are the range of x's, the range of y's, and the range of z's. Get a guy called diff f, who seems to be, the way the questions are at least working out, relatively nice looking, it's not that bad. And then put in your limits of integration, put in your diff, and then go and integrate with whatever variables you're using, either x, y, z, or cylindrical maybe, or spherical, which are the three go-to situations that you're likely to meet. Okay, let's move on. We're halfway through. Okay, let's see what this guy has in store. We're going to get the surface integral as always. And this time we are told that the vector field F is basically various powers of x, y, and z. Nothing too surprising there. And the surface S is bounded by the parabola z equals 1 take away x squared take away y squared and the x, y plane. Right, this one we're going to have to work on. If you went into GeoGebra and you sketched this guy, you would get one of these things. I think it looks a bit like an acorn, right? Now the xy plane is z equals 0, right? It's a floor. So I already know the limits of integration of z from the floor to the curved surface. Check. Now you might say, well, what about the x's and the y's? We need limits, ranges for them. What you have to imagine here is you're above the thing, looking downwards, and what would the shadow on the floor look like? Well, if you imagine this is their XY orientated, the way we would normally do it, wouldn't this be a circle? Now, what that tells me is that it's probably a good idea to go polar, right? When X, Y are circles, go polar. Second thing I need to know is, well, what kind of circle is this? Is it a radius 10? Is it a radius 4? Is it a radius what is it? I need to know that piece of information, and I get it from here. This is equal to that guy. When you think of what's that going to look like on the floor, you're basically saying, what does it look like in this case? Can you see that we now have a circle of radius 1? And that tells me then that I'm going to do an R from 0 to 1. And it's a whole circle. I don't see there any. No, it's a whole circle. There's no restrictions on it. Okay, so that one took a little bit more work to get the limits for X, Y, and Z, or in this case, R, theta, and Z. Are we comfortable with the logic of how that was done?
Yeah.
Okay, so now we move to, the next phase. Let's find the divergence. This guy, that guy, that guy. Your P, your Q, your R. So going to differentiate this guy with respect to X, and I get 18x squareds. I'm going to do this guy with respect to Y, and I'm going to get 3y squareds. I'm going to do this with respect to Z, and I'm going to get 15y squared. I was worried for a minute, but now I'm not, because do you see that you get that? And looking ahead, we get that, which in cylindrical coordinates is 18r squared, right? So we actually have the divergence of F good to go. So let's put all the pieces together, see what we end up with. Well, the guy I'm going to start with is the Z's. Now the Z goes 0, and it goes to 1 minus x squared minus y squared. If I'm going to go cylindrical, I don't want x's or y's. I only want r or theta or z, I guess, but I only want r or theta. So this fella here is actually 1 minus r squared. Are you comfortable with 1 minus x squared minus y squared becoming 1 minus r squared? That makes sense? It's a bit
Yep.
like, yeah, okay, good. It's a bit like doing this. That's all I'm doing, mate. Divergence, you're my friend. When you do cylindrical, it's R, right? Well, in this order, it's going to be Z first. Then I guess I'll do R, and then I guess I'll do theta. So R is going to be 0 to 1, and theta is going to be 0 to 2 pi. So tidy this up a little bit. That times that is 18r cubed dz dr d theta. And let's, oops, almost forgot. Let's do that guy, or at least part of him. With respect to Z, this guy is just 18r cubed Z. Evaluated Z equals 0 and Z equals 1 minus r squared. If you plug in that z for this, you get 18r cubed 1 minus r squared times 0, so I don't care, dr d theta. In this question here, we're pretty much done because there is no thetas. So I could separate it out into these two integrals. And if you think, where's that come? Oh, let's give this guy 18 now. This guy times 1, this guy times that one. This gets integrated using power rule. That's just 18 theta, and you are done. Question's pretty much over. Or you could have just did this integral, and then whatever the answer is, did the last integral, and you'd get the same result. Which, by the way, is a magic 3 pi. Which is a very elegant answer. Any questions?
Nope.
We good? Do you like the oh, what am I thinking? The flow or the structure to these questions? That they have a kind of A, B, C, D kind of thing to them. The only thing that varies is what the integral looks like, right? And you have to adapt to the situation. But apart from that, the flow is very consistent. Okay. Got, I think, 3 more to do. Version is 6 then. Same guy as everybody else is wanting. Vector field is unremarkable. They tend to just do polynomials, I guess, because they tend to play well and they tend to be relatively nice calculations. Now, the surface S that's going to generate our 3D solid is a cylinder. And the cylinder is x squared plus y squared equals 36. Now that's a 3D cylinder, right? It's an infinite cylinder going this way. And it's cut by the plane z equals y take away 6 and z equals 0. So can you imagine z equals 0 would be the floor, which would be a circle. And then the other one is some kind of thing like that. So you probably get an ellipse. So can you imagine a cylinder on the top half being cut at an angle, but the bottom being horizontal, right? So this region in here is the region E. So we need to go hunting for its limits of integration. Let's do the easy part. You've just told me what Z is. Now, if you look at this guy vertically and he hits the floor, won't it make a circle? And won't the circle have equation x squared plus y squared equals 36? Ah, how about cylindrical coordinates? Right, x squared plus y squared. So I'm going to turn this guy here into r, 0 to 6, and theta is the whole circle. And then I'm going to readjust the z's. If you are going to do cylindrical coordinates, then you are not allowed x's or y's. So z will go from 0, but not y take away 6. Can anybody remember what y is equal to in polar coordinates? It uses r and theta.
R sine theta.
That's the one. So r sine theta take away 6. Okay, we are ready. This guy, the flux, is equal to, since these are numbers, I will make no particular reason, r equals 0 to 2 pi. Theta equals, I might change my mind, but 0 to 2 pi. And z goes from 0 to r sine theta take away 6. And I, in all the rush to do this, forgot to get the divergence. So let's do it in here. It's the derivative of p with x, partial derivative of q with y, and the partial derivative of r with z. Your p, your q, and your r. Now, if you do this guy, check him. If you do this guy with respect to x, you get y plus 2z. If you do this guy with respect to y, you get 2y. And if you do this guy with respect to z, you get minus 2z. Oh, you get 3y. Oh, that's not bad. Although I can't use 3y, I need to turn 3y into 3r sine theta. Right, that's 3. Then I will do r, that's a z equals, by the way, dz, d theta, dr. Let's just tidy it up a little bit before we finish it. This mess becomes 3r squared sine theta, dz, d theta, dr. When you integrate this expression with respect to z, all you're going to get is this guy times z. You'll then replace the z by this guy in 0, the 0 won't matter. So you'll have all of this 3r squared sine theta times 3r sine theta take away 6. And that horrible mess you will multiply out. And then you will integrate it with respect to theta. It'll be really ugly. And then you'll integrate that answer once you put in theta is 0 and 2 pi. You'll do it one more time and you'll integrate it with respect to r. And yeah, you get, according to them, negative 972 pi. So according to the divergence theorem, the flux going through this three-dimensional shape. So you imagine vectors coming in, vectors leaving. What's the total net effect? It's a negative 972 pi. So fewer things are coming out than are going in. Or is that the other way around? Fewer things are going in than are coming out. Bit uglier, but it's still in the same theme that we've been doing, right? Just the limits of integration are getting messier and the integrations are less elegant because of that. Last chance, anything to be asked? Okay. Next fella, if you bear with me for just a little while. Involves a picture. So just try to make it a little bit cleaner. Actually, 8 and 9 both contain pictures. So I think it's ready. Let's show you. Maybe make it even a touch bigger. There. They have described over here all the various restrictions that you have on X, Y, and Z to generate this solid. So we need to find out what are the limits of integration that would make this solid happen. That sloping surface going this way, right, has the equation x plus 2z equals 8. I will rearrange this equation here. Right, just this guy here. I'm fighting the the click and tell me thing, right? Anyway, this thing here on the left, I will rearrange it to be z equals. And that will tell me the range from z. Z will go from this number or this expression to that. So far, so good. Now, the other pieces are actually easier to tell in the writing than they are in the picture. Can you see that y goes from 3 to 0? So that's the limits of integration. And that x, well, x, we've got to think about a little bit harder. X here is going to go from 0. Oh, gotcha. And it's, where is x? Here. And where does it finish? It finishes there. So what will x be? Oh, if you make z 0, x is 8. So that guy there's 8. So it's going to go 0, 8. So say that again. If you look at this equation and you make z equals 0, right, so that disappears. Do you see that the x value here is 8 and the other value we already know? So from that 3D solid, we managed to suck out what the limits of integration are going to be. And they gave us a surface, actually it's a plane, which is that guy. And I'm rearranging it to be that guy. And so that tells me the z's go from the surface to 0, because they told me 0. And they told me what y did. Y goes from 0 to 3. Okay. And then we figured out, hopefully, what x is going to be. And I'm just putting the thing back in here. X is going to be, well, let's see what the answer is going to be first. X is going, excuse me, 0 to 8. You know, the triangle looks something like that, and I figured out that was 8 and that was 0, but let me show you where it comes from again. This is the equation of the, you know, the sloping piece that's going like this. If you want to know what's happening when it reaches the floor, can you see the floor is a rectangle? All I need to know is what that x value is. Well, when z equals 0, you reach the floor. Can you see why I got 8? So there is our limits of integration. And in this question, I don't think I told you who f was again. F is x squared z, x z cubed, and y, the natural log of x plus 1. And now we're ready to go. The flux. And guess what? We're not ready to go. Then I almost forget to do the divergence again. I'll do a quicker version. This is P, this is Q, and this is R. Derivative of this with respect to x is 2xz. Derivative of this with respect to y is 0. Derivative of this with respect to z is also 0. So what you get is 2xz. Okay, so that's what the divergence is. So it's going to be x equals 0 to 8. Y equals 0 to 3. Z equals 0 to 4, take away a half x. The divergence, do a z, do a y, and do an x. We have done enough triple integrals to fight your way through that, right? It's not that bad. Nothing really is separable, so you'll have to do it the long and hard way. And I was looking for the answer, and that's a surprise. It's actually a nice number. Evidently, it's 256. For the computer people amongst you, that's quite an interesting number. It's the power of 2. I believe it's 2 to the power 8. Right, so what was different about this? They gave you a shape, and from that shape, you had to figure out what the limits of integration were. So we're now on our final guy. Question 8. So instead of doing all this jumping to and froing, I'll try my best to sketch what the thing looks like. Okay. There's a parallel to the y-axis line that goes here. There's a nice little curvy thing that kind of meets here. Then it goes all the way across and then down, and all the way across and kind of down. Can you imagine what that shape looks like? It looks a bit like a shoehorn, right? A kind of thing you would stick under your door to keep your door open, right? It's kind of wedgy thing. Now, the surface here, this flat curved bit, is x plus z equals 1. This thing here, and I've made it more rectangular than it is, it's actually curved like this. This surface on this side is x equals y squared. And do we know anything else? No. Oh, and we know z is 0, but that's pretty obvious, it's the floor. So somehow or other, we're going to figure out what the limits of integration are that would make this horseshoe shape. I'm going to focus on the z's. Well, if x plus z equals 1, then that makes z 1 take away x. And since the shape finishes on the floor, that makes z equals 0. So I now have my limits of integration for z. If we now focus on what does this shape look like when you project it onto the floor, and you have to be careful about orientation here as well, because it looks back to front. It's actually x equals y squared, do you see it? Now x equals y squared looks like that guy. So far, so good. Now, I know where it starts, but don't I need a finish point? So can you imagine this part is that guy, right? I need to know what number this is the x-axis. I need to know what's that guy, this is the y-axis. And I'm going back to here, because if z is 1 minus x, and you make z 0, which is the floor, you will find out x is 1. So this is the half curved shape that would be the equivalent of this bit here. And my picture's getting really ugly now. But I've pretty much got what I need. If you are going to do this shape, you probably should go that way. Or you want to go the other way. I would go that way because this number here is 1 and this number here is negative 1. So I should be able to do y goes from negative 1 to 1, which is this guy. My screen flickered there. Is everything okay, guys? Because I could be talking to myself. Yeah, okay. And then what is the x's going to do? Well, the guy on the right-hand side is big, and the guy on this side is y squared. So there we go. So this curve, because of its orientation, it was better to do horizontal lines. So y goes from negative 1 to 1, and x's go from here, which is x equals 1, to here, x equals y squared. So there are our limits of integration. Now the vector f is 7xy take away z squared, 5x cubed square z, and 7xy plus z squared. And so let's find the curl of f, because that's the last piece of the puzzle that we need, which is this guy, that guy, And that guy. If you do this expression with respect to x, you get 7y. If you do this guy with respect to y, you get a big 0. And if you do this guy with respect to z, you get a 2z. So the curl ends up being 7y plus 2z. Check that out. And it is. So we should be able to put it all together then. So the flux is a triple integral. And since this has got x's and this has got, well, x's in it, and this is x's has got y's in it, and this guy has got numbers, I now have to decide the order of integration. Well, let's do the easiest one first. Y is numbers. Great. Now, this one has x's in it, and these x's have y's in it, right? So how about z equals 0 to z equals 1 minus x, and then x going from y squared to x going to 1. Now let's see what that would do. If I integrate this, I'm going to get x's. If I integrate this, the x's will turn into y's. If I integrate this, the y's are the only guy left. That will work. And the guy we're going to do it to is 7y plus 2z. And I've decided z followed by x followed by y. Let's do a little check. I wonder if I could switch places. If I did x first, I would get y's. And then if I put this guy second, I would get x's and y's. That would not work, right? So that's the only feasible combination where you end up with a number when you're finished. And that guy is
For
just
the-
a very...
For the y limit,
Mhm.
is that you always go left to right on that, or is it?
small
why
a
don't
big.
why don't you go from 1 to y
Negative 1.
squared?
What,
Or,
this
I
one
mean,
here?
X. Yeah, that one. Is that an X?
Okay,
Sorry.
yeah, that's an x. Okay, that's an x. If you look at this picture here, I'm going to scan through this two-dimensional shape horizontally. So because I'm doing horizontally, the y's are 1 and -1, so that's that. And this typical rectangle has on its big side a straight line 1, so that's where that came from. And on this side, the x coordinate would be y squared, so that's where the y squared comes from. So it's going from a 1 to the curve, a 1 to the y squared.
Okay.
Normally we do 9 times out of 10, don't we do shapes that way? In which case it's top to bottom. But if you have to, sometimes you have to. If you go left to right, isn't the big guy the furthest to the right? In this case, just 1, right? It's always 1. It's a straight vertical line to the curve. In this case, x equals y squared. Cool. Now, I'm going to leave that guy because he's just ugly and long, but he's just a triple integral like you've done lots of times before. And I'm taking Webaside's word for it. It's 32/105.